So in this section, we are going to introduce a different method to derive the small signal model of the CPM controller. So the method is called the average switch model. So we are going to select a different topology. Here we use the buck converter as the example. So averaged switch model. So which is indeed one of the modeling methods we learned before, right? Before, for the pulse-width modulated control. And here we can deploy this method into CPM control. So we use the buck example. So first, let's plot the schematic of the buck converter. So here is the input voltage source, VG, in time domain, right? Here is Q, D, L, C, R. And output voltage is denoted as VT. So here we first plot the full signal, right, without the cap. And for such a buck topology, we can extract the switch network. So here is the switch network for buck converter. And on the input port, we can denote its input port current and voltage. So here is input port I1, and here is input port voltage V1. And on the output port, we also denote its voltage and current. Here's V2, here is I2. Okay, so for continuous conduction mode, CCM, operation for buck converter, we know that the average input port current, I1 average, will be equal to the D times the average output current. And secondly, for the voltage relationship, the average output voltage, V2, will be equal to D times average input voltage. So here we consider the current programmed control, CPM. So for CPM, we know that the inductor current is approximately equal to control current. So we will consider that I2 equals to IL and approximately equal to controlling current, right? So that the I2 average can also be approximately equal to average controlling current. So we can insert the IC term into the previous DC model of the buck converter, IO. Okay, now let's look at the Formula 1, right? Formula 1 and Formula 2, we can combine them together to find out the expression for I1 average. So basically, combining those two, we can eliminate duty cycle, right? After eliminating duty cycle, so we'll see that I1 average equals to the product of the I2 average and V2 average divided by V1 average. And right, the I2 average equals to IC average, right? So we replace I2 by IC average here. So this will be times the ratio between V2 and V1. Okay, so this means that we can rearrange this formula by multiplying both sides by V1 average, right? So on the left-hand side will be the product of I1 and V1. And on the right-hand side will be the product of IC and V2 average. So if we look at here, right, the product of I1 and V1 average, this is indeed a power, right? So this is the expression for power. So this means that this equals to the average power absorbed by the input port, right? Input port. So this result indicates that the switch network maintains a power sink behavior. Power sink behavior. So we can model this switch network by a power sink, right, on the input port side, right? Here is the power, it sinks power. So I can plot the equivalent circuit model here. So average, right? Average. And here is average input current. So to the input port, this is a power sink behavior. So here we use a power sink. To denote, right? To denote. And on the port 2, right? Port 2, you will see that it's just like I2 equals to IC. So IC is the external controlling signal. For the power circuit itself, IC can be treated as an independent current source. So this is a current source behavior. So the output port can be replaced by an independent current source. So whose in current is IC average, right? And the power is transferred to the independent current source, P. So that's the equivalent circuit model for the switch network. And for the rest part, right, we just plot it as it is, right? So here is the low-pass filter network. And here is the output voltage. Right, here is the V1 average. And here is the I2 average. And here is the V2 average. So that's the equivalent circuit model for CPM, right? For CPM buck converter. But this is basically the averaged switch model. And we want to derive the small signal AC model, right? So the procedure will be pretty standard. we perturb and linearize. So first, we perturb it. So we perturb those average quantity with small signal variations. For example, V1 average is perturbed to be equal to the DC quantity plus small signal AC. And I1 average is equal to DC quantity plus small signal AC. And the V2 average, DC plus small signal AC. I2 average, DC plus small signal AC. And also the controlling signal can also be perturbed. The average IC is equal to DC quantity plus small signal AC. Then we insert the perturbed signal into the original formula here, right? Formula here. So you will see that left-hand side is the product of V1 plus V1 small signal and I1 plus I1 small signal. And the right-hand side is product of IC, right? IC. And V2, right? V2 is here. So we can decompose this equation. We eliminate the higher order harmonics, right? Only keep the DC terms and the first order AC terms. So basically, the DC term should be equal on both sides. So DC terms will be rather simple, right? Left-hand side is V1, I1. And right-hand side is IC, V2. So this gives you the clue for the DC model, DC relationships. So we can derive that I1 equals to D times IC. This is because V2 average is the output voltage equals to D times in V1 average, right? V1 average. And next, we look at the first order AC terms. So we only keep the first order AC terms. Left-hand side will be I1 small signal. And right-hand side will be IC small signal times V2 over V1 plus V2 small signal times IC over V1 minus V1 small signal times I1 over V1. So that's the linearized equivalent model for the Buck converter in CPM. And the last one will be the output port. For the output port, we just look at here, right? It's pretty simple. Basically, the output port current is I2, right? So output current is equal to the controlling current. So it is with the small signal AC part, right, equal to the I2 small signal. Okay, now we have erased the blackboard. Now let's continue to process this resulting equation. We denote this equation as equation star. So specifically for Buck converter, right, we can introduce the DC relationships for Buck to simplify this expression. So for equation star, and also for Buck, right, we learned that for Buck converter, the V2 will be equals to D times V1. And also I2 will be equals to IC, right? In current program mode. So this will be equals to V2 over R, which is the DC average current, right? DC average current will just be equal to the resistor current. And thirdly, we will have that I1 equals to D times I2, right? This is, we have derived here, right? So by inserting those three DC relationships into formula star, so we can derive that the I1 in S domain, right, will be equal to D times, right, this is D, IC, plus this will becomes D over R, V2, right, V2. And this one, right, I1 over V1 is modified to be minus D squared over R times V1 in S domain. So again, for the buck converter, the V2 small signal in S domain is equal to the output voltage plus the voltage drop across the inductor, SL times. So this is indeed from the KVL equation, right? So this voltage equals to this voltage plus the inductor voltage. That's how we obtain this formula. And then we can insert this V2 expression into here to eliminate V2 in the top formula, right? So finally, we can reorganize this formula to be I1 small signal in S domain equals to D times 1 plus SL over R times IC S. So this is a combination of IC terms here and here, right? Then for this this part is changed to be V, right? So D over R Vs. And this one is modified to be minus D squared over R times the line input So by utilizing this small signal equation, we can establish the small signal circuit model for the input port, right? So basically, we can re-plot this figure in small signal AC format. So here is input VG cap. And for the power source, right? Power source in average mode, it is linearized to be this formula, right? So I1 small signal equals to the sum of three parts. So it means that it can be treated by the parallel of three circuit components. For example, here this will be an independent current source. Whose value is like D times 1 plus SL over R IC cap. And then this one, right? This one can be modeled by a controlled voltage source, controlled current source. So this is D over R V cap, because it is controlled by the output port voltage, right? And this one can be modeled by a resistor, right? Resistor. So the coefficient will be the resistance. The resistance will be equal to minus d squared over r. R over d squared. So you will see that this is indeed a negative resistance, right? So this is not a practical resistor, it's an effective negative resistance behavior. So we still use the resistor symbol to represent it. And for the output port, it's like here is perturbed results, right? Perturbed and linearized results. It's pretty simple. We just use a small signal AC current source to denote this current source. IC cap, and here is the I2 cap. Here is the I1 cap, V1 cap, and here is the V2 cap, right? So beyond this switch network, we will keep the IOC network as it is. So here is the L, filtering capacitor and load resistor. So that's the linearized small signal model for buck converter in CPM. And based on the obtained small signal circuit model, we can derive its transfer functions. Right? For example, first we care about is the control to output transfer function. So which is defined as the ratio of the output voltage and the controlling current under the condition that the line input is 0. So you will see that if the line input is 0, here it will be short circuit, right? Short circuit. So actually, the output voltage will mainly determined by this independent current source. So output voltage equals to the IC times impedance of this RLC network, right? So basically, it is the ratio will be equal to R parallel with C, because the voltage just equals to IC times parallel of R and C. So the transfer function is just R parallel with C. And next, let's look at the line to output transfer function. So line to output transfer function is defined as the ratio of the output voltage and the line input under condition that controlling input is 0. So for this time, controlling input is 0 means that here is opened. Here is opened, right? So the output will be just equal to 0 because there's no excitation here. Opened, so output will be 0 for sure. So this means that the line disturbance will not affect output impedance, output voltage at all. And the last one is the output impedance. Right, output impedance will be simple, just the R parallel with C in series with L. So SL plus. So that's the CPM, small signal model for buck converter under the assumption that the controlling input is equal to the inductor current. Okay. So based on the material we delivered in this section, we can see that through the average switch model, we can check the CPM, switch networks, energy flow process. And, but those analyses are based on the assumption that the IC equals to I/O. And for more accurate analysis, we'll discuss in the following lectures.